Hello everyone, I'm Norman Wildberger. In today's famous math problem, we have a rather special situation because we're treating the most fundamental and important problem in mathematics, at least in my opinion. Natural question that will be on your mind is, what is this most fundamental and important problem? I think it's part of my duty here when laying out all these different problems that we're going to be looking at. Some of them are interesting, some of them are curiosities. They range over a lot of different territory. So it's nice to have that aspect, but it's also nice to have an idea of the relative positions of problems, in particular to identify clearly which are the most fundamental and important problems. So this is a real core problem that we're talking about today. It's fundamental in the sense that it lies at the base of mathematics. It has a sort of elementary aspect and also a wide-ranging aspect. It affects a lot of different mathematics at a very foundational level. It's important because, first of all, it connects with many areas, but we'll also see that it crops up historically in a lot of different places. A lot of famous mathematicians have, at some point or another, wrestled with this problem, or some aspect of it. And it has lots of consequences. So the way we answer this problem affects a lot of different mathematical theories. All right, so without more ado, little drum roll. The most important and fundamental mathematics problem is, well, here it is. Famous math problem number 19. How to model the continuum. How do we get into mathematics the idea of continuity? In particular, how do we model the continuity that we see when we look at a line? Now, this is a rather open-ended problem, and the difficulty level is ranging over a wide range. At some level, it's a solved problem, and we're going to talk about that aspect of it today. Difficult, but not overly difficult problem with a level of 4. And it goes up to very, very difficult problems, perhaps ultimately unsolvable problems. So there's a wide range of possible answers to this problem. It goes back, of course, historically, to the ancient Greeks at least, to the work of Pythagoras, to the paradox of Zeno, to the work of Eudoxus. It was also very great interest to Archimedes, to Aristotle, and other thinkers. This problem lies at the heart of geometry and analysis. But in fact, it also has a lot to say about modern algebra too. It's intimately connected with physical questions, having to do with time, quantum mechanics, even the large-scale structure of the universe. These days particularly, it's intimately tied up with set theory and axiomatic approaches to mathematics, some of which I think are rather problematic. The question is really a basis for a lot of more advanced disciplines in mathematics, in pure mathematics especially. Algebraic topology, differential geometry, algebraic geometry, linear algebra. In fact, a lot of areas. I could have listed more here, aside from, of course, geometry and analysis. And very interestingly and prominently, this question connects with modern computer science. We'll see that as we progress a little bit later more deeply into the question. I believe this is a fundamental kind of open-ended problem that's not going to go away. Really, really important problems can never be fully solved. We can make progress towards them, but there's always something more that unfolds as we learn more. I believe that in 1,000 years from now, this will still be a core problem. In fact, it still may be the most important and fundamental problem in 1,000 years. One very interesting aspect of this problem is that nowadays, around the year 2014, this problem is largely invisible to most math students and, in fact, most mathematics professors. That's because the modern pure mathematician largely believes that this problem has been solved. This is an erroneous idea, but it's a very common one. They think that the continuum is modeled by the so-called real number line. They think that there is something called the real number line, and that answers the question of what the continuum is. The real number line is usually presented in a picture, something like this, with integers and fractions placed where you would expect, and sort of arrows pointing to particular so-called irrational numbers like √2 or e or pi. But the actual specification of, first of all, these irrationals and their arithmetic, and the proofs of the laws of arithmetic of these so-called irrational numbers is rarely laid out completely. There's various sort of cliches that people learn. Students learn to recite the statement that a real number is an infinite decimal, or perhaps a Dedekind cut, or perhaps an equivalence class of Cauchy sequences, and there are other possibilities too. But when you actually look carefully, try to find a place where the theory of any one of these is clearly laid out, well, then the logical problems become pretty obvious. So it's a very unfortunate aspect of modern mathematics, and it's a very big step for students to start appreciating that the status quo, the orthodoxy that they have been taught, is in fact really misleading and misrepresents the historical importance of this absolutely crucial question. So the modern orthodoxy is in fact seriously in logical error. Now, this is a very important issue, of course, and I deal with it and am dealing with it at length in my Math Foundation series. And I don't have time to summarize everything there in a few lectures here, but I am going to give you an overview of some of the logical problems. But I'd like to emphasize that you can test this for yourself. Okay? So the way to test it for yourself is to actually look for a place where the theory of real numbers is properly laid out, and then actually read it. Okay? It's remarkable that if you open most calculus texts, and for most calculus texts, the real number line is the absolute fundamental framework on which modern analysis is built. But you look for a chapter that lays out the arithmetic of real numbers properly and carefully and completely. And uniformly, you will find such a chapter missing. There will be references to it. There will be some quick statements that summarize some of the things that hopefully are true about real numbers. But for an actual complete laying out, you will not find it. A few years later, when you graduate to a course in modern analysis, the same situation arises in modern analysis texts. And you can check this out for yourself. You can open up modern analysis texts and look for the chapter on the theory of real numbers. There almost never is such a chapter. Occasionally there's something in an appendix. Then when you look carefully at that appendix, you see that as you look more and more carefully, the logic starts to recede. That you start noticing that they're already assuming things that are pretty close to being what they're supposedly constructing. We're going to talk a little bit more about that, but you can check it out for yourself. That's the point. You don't have to take my word for it. Open up the book, see where is the theory of real numbers, where it's properly laid out, what the actual objects actually are, how you do arithmetic with them, in other words, proper definitions of the operations, and then proofs of the laws of arithmetic. I claim nowhere on planet Earth in the year 2014 is such a thing laid out, which makes a lot of the mathematics that's built on the real numbers a logical sham, if I'm going to be completely honest. All right? I mean, honesty is what I'm sort of interested in here. It's a logical sham. And it's an unfortunate situation, so one of the things I hope to do here is to convince you that this is, in fact, an open-ended problem. It's still an open problem. There's still more to be done. There's a lot of connections with computer science that we need to understand before we can really get at a grasp of what this problem is doing. But, on the other hand, there is also a solution that already exists. There's a solution to the problem that already exists, a very workable basis for mathematics that goes back, of course, to the ancient Greeks. So the history of the subject is intimately connected, and we are going to have a lot to say about the development of this interesting question, and I hope that in the next few videos you're going to learn quite a lot, not just about this question, but also about associated and related areas. So when ordinary lay people think about the word continuous and the notion of continuity, then often time and motion are somehow involved in their thinking. And this is very natural. So a natural question is the continuous aspect of time mathematically the same as the geometry of a line? Our sensation of the passage of time is a model of continuity, as is this motion on a line. Are those the same kinds of continuity? Where does motion itself fit in to our understanding of the continuum? Which brings us to this other question. What's the connection here with physics? Does physics necessarily enter the discussion? Do we have to worry about the actual structure of space? Does that dictate the mathematical form of a line? So 20th century physicists have, of course, penetrated to smaller and smaller scales. And they've become very aware that the physical world that we live in is quite different at different scales. If you blow up by a factor of 10 or reduce by a factor of 10, then typically what you're seeing looks quite different. There are probably roughly about 60 orders of magnitude between the very smallest things that we can observe at sort of the Planck scale and the very largest scales that our telescopes can get at in the universe. And every time we go up by a factor of 10, things look different. So there's certainly a non-kind of homogeneity as far as scaling goes when we actually think about the physical world, the physical space that we're living in. Does that necessarily reflect something about the mathematics, or is the mathematics completely independent of the physics? It's a question. This question of homogeneity is interesting. Does the continuum look the same in all directions? You know, a line in this direction, is it really the same as a line in that direction? What about the scalability? Does the inherent inscalability of the physical line manifest itself in an inscalability of the mathematical line or not? So these are somewhat sort of philosophical or meta-mathematical questions, but they still sort of frame our understanding of this question. We ultimately want to do just pure mathematics, independent of physics, but still when we're setting things up, we need to be conscious of this kind of questions and other related ones. So there's a lot of different ways of thinking about this situation. Very interesting connections with physics, with philosophy, with cosmology. All right, so I've said a few times that this problem, along with most great problems, has an open-ended aspect. And if we put aside our ingrained assumptions, then we can recognize that there are a number of different kinds of continuities that we might be considering as fundamental. But it's not self-evident which one is sort of primary and which one we should be focusing on primarily at the beginning. For example, a segment or a line segment is an obvious kind of thing that we want to model in mathematics. But so is a curve. And it's not entirely clear that the continuity of a curve is completely the same as the continuity of a segment. Or maybe we should consider segments that go on in both directions, so-called lines. And maybe that's a better model that we should be focusing on. And then the question is, well, is this line or this line the same? Which line should we be considering? Or perhaps we really want to be working in a plane. Perhaps a plane is a better framework for thinking about continuity because it's a little bit closer to the geometry that we know about. And well, once we go up in dimension, we can start thinking about space. Maybe we should be also talking about the nature of the continuum spatially in 3 dimensions. Or perhaps, if we are able to, 4 dimensions or higher. So there's a whole variety of continuums, and they have some kind of relation with each other. Lines sit inside planes, planes sit inside 3-dimensional spaces, and so on. And then in sort of completely different direction, there is this notion of time, and the clock is another model of continuum, and how that fits in with the space is, again, almost a meta-mathematical question. But even at the level of mathematics, there are some options about which direction we should look at sort of first. Most modern students these days will think of the continuum as being like a number line, and they will take a position which was really enunciated by Descartes in his great revolution of introducing numerical coordinates into geometry. This is the preferred point of view these days to tackle the problem of the continuum algebraically or arithmetically by introducing arithmetic or a number system to model the line. But it's interesting and useful to go back in time to the earlier period, to the ancient Greeks, and to recognize that their notion of the continuum was in fact quite different and was not based on a prior understanding of arithmetic. I think this is a really good thing for us to discuss for a little while, because it brings in some concepts that are not so familiar these days, and some of them which are actually quite interesting and useful even for, say, high school arithmetic, high school mathematics. So I'm going to go back to antiquity and ask the following question: how do we construct a ruler? Going back to the days of the Pythagoreans or Euclid, and I'm going to work in the context of planar geometry. So here's a line that we've drawn with a straight edge, and let's talk about how we might get at what this thing is by thinking about how to make a ruler. That's a very good place to start a discussion of the continuum. And I would like to do a little bit of a twist on Greek geometry. The Greek geometry that everybody knows is Euclid's geometry, which he laid out in the book The Elements, and that has dominated the thought of, well, mathematicians since that day about the framework of geometry. But in fact, there was, or is, a variant of Greek geometry called affine geometry, which the Greeks only roughly explored, not very much, but it's actually a more primitive or simpler geometry than that of the Greeks. It's really the geometry of a straight edge. So you're given a straight edge, something like this. You have to ignore all the markings, okay? Pretend that it's just a surface without any markings. And together with a notion of parallelism. So we assume that given any line like this one, we can draw parallel lines. You might think about a draftsman's table that has a mechanism, a physical mechanism that allows you to put a line like this at any angle, and then allow this line to be translated, making it very easy to draw parallel lines. Then you have one different line, you put it in position like that, and then you can translate it, making parallel lines very easily. So the affine geometry you can think of today as just the geometry they get by you start with a plane and you're only given a straight edge together with this ability to make parallel lines. But in particular, there are no circles, and in particular, there is no notion of perpendicularity in this geometry. It's a simpler kind of geometry from that of Euclid. And this is a very good place to start because we can ask the question, we can answer the question, how do you make a ruler? And I want to show you. It's quite instructive. All right, so here is the baseline that we want to make a ruler out of. And we'll start by, say, drawing 2 points. Okay? And we're going to sort of use that as the basis for a system. All right, so the first step that I'm going to do is I'm going to draw a line parallel to the given line. So let's see, try to make it as parallel as possible. All right, so this line here that I've drawn now is supposedly parallel to the original line. And now I'm going to take these 2 points, and through the first one I'm going to draw another line. And it doesn't really matter where it is. And then I'm going to draw a line that's parallel to that one through this second point. Like that, all right? So these 2 lines here were parallel, I'll denote that like that, and these 2 lines are parallel, we'll denote that with these double arrows. All right, and now we want to make a ruler. How are we going to do that? Well, I'm going to draw some more parallel lines. So here's a new point, and here's another new point, and I'm going to connect this new point with that old point down there. There's another line. And then through this point here, I'm going to draw yet another parallel line that's parallel to the one that I've just drawn. All right, so there we go. Now I can, in my mind, I'm thinking that this segment here that we started with has been reproduced up here. Okay, it's the basic idea. This segment here has been reproduced on this parallel line. But now I'm going to translate, that's essentially what I've done, translate it again to down here. So down here, so that this segment is the same as this segment, and this segment is the same as this segment, so that what we have now is two equal segments on the original line. And now we can repeat this construction. So I can just do the same thing to these 2 points as I did to these 2 points. So here I can draw a parallel line, maybe something like this, and I get a new point here, and then from here I make a new parallel line, and I can continue in this way to create a series of equally spaced points on our baseline, our original line. Let's call it L. Now along the way, I'm actually also constructing equally spaced points on other lines. For example, if I look on this line here, then these additional points here are also forming a kind of a equally spaced group of points on that line there. All right, so we're capable of doing this, but that's still not really such a good ruler because we haven't been able to make finer subdivision. So suppose we wanted to divide this segment into, a certain number of equal sub-intervals. How could we do that? Well, here's a nice trick. Suppose, just for the simplicity, that I want to divide this into 3 equal pieces. Okay. So what I can do is I can take the 3 equally spaced segments on this line here. So there's 1, 2, 3. And I can join this one with this one. All right. And now if I take that line that I've just drawn and make a parallel line that's going through this one, it's supposed to be a parallel line, and then one more parallel line through this point here as well, well, then I've gotten some points down here, and I've gotten 3 smaller segments where I just had 1 to begin with. And I could easily, just as well, have divided this into 5 or 10 by taking more points along here and drawing parallel lines in exactly the same way. And so I think you can experiment a little bit, and you can see that by combining these techniques we can then create a ruler with as fine a subdivision as we want, and that extends as far as, well, we feel like it, subject to the accuracy of the tools at hand and the size of the paper that we have. So this is then an initial model of a kind of continuum, that we have points on a line and we've created some kind of ruler, which of course these days we would think of as being identified with the numbers. Well, that's number 0, and that's 1, and that's 2, and that's 3, and so on. And these numbers here are 1/3 and 2/3 and so on. But the ancient Greeks didn't so quickly assign numbers to points. They just worked with the points themselves. And I want to kind of carry on a little bit with that maybe naive, much more ancient way of thinking, to get a sense of how the ancient Greeks thought about the continuum. All right, so although I didn't say it, the main tool that we're kind of using in that construction and that kind of thinking that goes going on in the affine plane is really similar triangles. So this affine geometry setup of allowing us to draw parallel lines allows us to define the rational number line geometrically. And the main tool, similar triangles, which allows us to compare equal ratios of segments. And here is just a summary of the basic situation that one exploits in affine geometry and the notion of parallelism. So suppose we have two lines, say L and M, which meet here. And suppose we have 2 points A and B on this line L, and maybe 2 other points C and D on this line M, with the property that this line AC and this line BD are parallel. All right. Now, when we talk about a point like this, we generally think of a number associated to that. But the ancient Greeks rather thought about segments as being the essential objects, not numbers. So instead of thinking about this A as being that point, they would rather have thought about this segment. So I'm reducing it down here. There's the segment A from here to here. And say from here to here, that's the segment B. Okay. And correspondingly, this segment here, I've copied it more or less there. There's C. And this segment here is segment D. Okay, the basic property here of this similar triangle story here is that, well, this triangle and this triangle are similar. And what that means for us is that the ratio, or the proportion between the segment A and the segment B, so the proportion between this segment and this segment, is equal to the proportion between this segment C and this segment D. So in proportion language, A to B, that proportion equals C to D. There's no way of expressly talking about the relationship between the length of A and the length of C. Okay, so in affine geometry, there is no notion of length that's suitable in all directions, because we don't have a compass to move length in one direction to an equal length in the other direction. In Euclidean geometry, yes, but in affine geometry, no. But what we can do is we can compare the ratio of these segments to the ratio of these segments. Now, the modern mathematician would say, well, what we're talking about is the ratio between the number A and the number B. So A over B equals C over D. Or they might say we're talking about the ratio between the length of A and the length of B, and the length of C and the length of D. But the ancient Greeks didn't think about it that way. They thought just about the segments themselves. Okay? It's the ratio between this segment and this segment as compared to this segment and this segment. And the ratio to them had meaning in the same sense of the ruler that we constructed on the previous slide. One segment can be reproduced. And then if you have the combination of those two equal segments, well, then that long segment is twice the first segment. So it's an arithmetic really with segments that we're talking about. It's a different kind of idea about the nature of the continuum. But it's a very old and valued way, because that's the way the ancient Greeks thought about it for hundreds of years. It's really at the heart of Euclid's thinking about things. Note that we do not state that A to C equals B to D. With our modern notion of lengths, yes, this would be also a formula from similar triangles. But we don't want to compare this segment to this segment because they're in different directions. And there's no way of comparing their relative sizes or essences in affine geometry. Okay, so if we stick with this sort of variant of ancient Greek thinking called affine geometry, which is really properly a precursor to Euclidean geometry. It wasn't actually historically a precursor, but it's a logical precursor in the sense that it's a simpler and more elementary geometry. Then we find, using the ideas, the constructions that we've been talking about, that we can create an arithmetic of points on a line. And it's really the same kind of arithmetic as the rational number arithmetic that you all learn arithmetically, but it's a purely geometrical kind of arithmetic. Now, the ancient Greeks didn't quite think about things this way. This way of thinking was really more a 19th century development, often associated with the names of von Stout and Hilbert. And maybe also in some other settings, in particular in a projective setting. So I'm giving you an affine version, which I think is the easiest one to understand here for us. Okay, so the claim is that if we're just thinking about segments on a line, say this line here, that we can use the constructions and the thinking of the previous slides to define both addition and multiplication in the context of these segments. So let's have a look at how that works. It's quite interesting. So here's our line here, and we're going to specify a particular point. Let's call it 0. Okay, it's just a symbol. And then we have two other points, A and B, which we refer to as points, but the Greeks would rather have thought of the corresponding segments. So we're always talking about segments from O. So that's the segment A, and this is the segment B. And now I'm going to show you how you could define a new segment, which you might call A plus B. And the idea is, well, we've seen it really essentially already. We make a parallel line to the original line. We draw any line from O to meet that parallel line, and then another parallel line to it, just as we did before. And then the idea is that this segment and this segment are going to be equal. They're translates of each other. And then if we translate this segment down to B, we can do that by joining this to this, and then drawing a parallel line, that green one there, through that point. Okay, so we draw this one, and then we draw this one, and then this point that we get here should be called A plus B, because this segment here is the same as this one here, which is the same as A. So what we've got here is the segment B and a copy of the segment A for a total of the segment A plus B. And notice that we can define this arithmetic purely geometrically using only constructions with our tool for making parallel lines. A little bit more sophisticated is multiplication. So here's multiplication in this setting, and for that we need not just a 0, but we also need another distinguished number, which we're going to call a 1. Okay, so it's just another special point, or maybe segment, on the line. And now I'm going to show you how to multiply A and B. So this is A, representing that segment A, and this is B, representing that segment B. Then here is A times B. Okay, what do? Well, we draw an auxiliary line through O, and then we draw a line from 1 to this line, meeting in some place. And then we draw a parallel to that through A. So if we just look at this situation here, it's the same thing we had in the previous thing. Then 1 to A is equal to this to this. Or in our language, this is A times this, so this one is A times this. Okay, and now what we're going to do is we're going to draw a line from here to here, and from here to here, parallel to this one. Then, well, the same kind of reasoning. This to this is going to be this to this. This is 1 to A, and this is 1 to A, then that means this is going to be A times B. All right, so we could define multiplication this way, and we could define addition this way. This is something that we could do when we're teaching primary school children arithmetic, but it's a kind of a geometrical arithmetic. It's never done this way, or I'd never heard of it being done this way, but we could possibly do it. So that students would actually make calculations not with pen and paper with numbers, but they would make calculations by drawing parallel lines on a piece of paper. So here's 3 exercises for you to think about. Okay, rather interesting. So first of all, show in a similar spirit how you might construct A minus B and A divided by B. And then try to verify empirically the commutative, associative, and distributive laws. Right, so you could take the law A times B equals B times A, or A plus B plus C equals A plus B plus C, and so on. And you could take each one of those laws and actually verify it in a particular situation. You might have A and B. You could calculate A times B, and you could also calculate B times A, and see whether you actually got the same point as a result. And then a more subtle thing that probably would suggest itself to you once you've played around here a little while is how do we actually know that these operations are well defined in the first place? Okay, so these operations depended on some choices. So for example, to define A plus B, I first chose a parallel line. I could have chosen any parallel line. And then I chose this line rather arbitrarily. I could have chosen any line. So what if it happens if I change this line and do the same thing? Do I get that same point? Well, we better, but we have to check that that's actually the case. So potentially we could do arithmetic this way, and maybe on some other planet in the universe, young amphibious creatures out there on some planet learn arithmetic this way, purely geometrically. And this fiddling around with 3 over 4 plus 5 over 6 and getting your calculator would be very alien to them. So this is a way of establishing the arithmetic of the continuum, purely geometrically, which is more in the spirit of the way the ancient Greeks thought about the continuum. This is a very good way of starting to think about this question, is by going back to the ancient Greeks and thinking about how they thought about things. This is not exactly how they thought about things, but it's in that spirit. They thought about things, their multiplication was different. They thought about multiplication is a two-dimensional operation. So if they wanted to multiply the segment A times the segment B, they thought in terms of making a rectangle whose sides are A and B, and then computing the area of that rectangle. Because they were able to use a compass to transfer this segment A in this direction to an equal segment in a perpendicular direction. And then once you've done that, okay, you can make a rectangle and you can talk about area. So this is not the way the ancient Greeks thought about things, but they could have. In an alternate, slightly different history of the world, the Pythagoreans could have developed an arithmetic in this affine way, and that would have been in some ways preferable to what actually happened, because this affine geometry and the closely related projective geometry are really more fundamental, to be honest, than Euclidean geometry, more elementary. Okay. And of course more in keeping with modern linear algebraic ideas. Linear algebra is pretty close to being affine geometry, as those of you who are watching my Wild and Alge series on linear algebra will know. So now we have an answer to our famous math problem. The first and foremost answer to the question, how do we model the continuum, is the continuum is modeled by the rational number line. This is an answer, and it turns out to be a very good answer. It's the first answer that you would think of. It's the answer that was implicit in what the ancient Greeks did. We might even call it the Pythagorean solution, because the Pythagoreans were very keen on natural numbers and ratios of natural numbers. Fractions were close to their heart. But we've seen that we can have two dramatically different views or approaches to this rational number line. The geometrical one that I've been talking about in today's lecture via affine geometry, and the by far more familiar arithmetical one that you'll all have learned in primary school via natural numbers and quotients of natural numbers, where one defines addition in this fashion, where we define multiplication in this fashion, and where we establish the laws of rational number arithmetic or fraction arithmetic built on a prior understanding of the laws of arithmetic for natural numbers. So we have a kind of hierarchy of arithmetic: natural numbers, integers, fractions, rational numbers. Okay. And that's the one that everybody's familiar with, and that's sort of the standard thing you would think about. But so it's important to realize that there's an alternate possible way of thinking about the whole subject of what the rational number line is. It's a geometrically constructed thing once we have an appropriate theory of affine geometry, and I haven't really spelt out what that might be, sort of left it to you as a challenge to figure out what that might be. Okay, but our famous math problem does not end here, because there are other answers too. The rational number line is a very good solution, but we're going to see that sometimes we want a richer notion of a continuum. So there's going to be a possibility of having a whole variety of continuums in ascending order of complexity and difficulty to construct, with perhaps different applications. And we're going to be talking about how that might go in future videos in this discussion. Okay, so while the arithmetical approach to the rational number line is well understood, this geometrical approach that I'm sketching here deserves more attention. So this is a really interesting challenge that some of you might like to think about, is to go back to that framework of arithmetic on a line done geometrically and try to establish those various laws of arithmetic as theorems rather than as empirical results. So instead of doing something physical, drawing and then noting that we get the same thing if we do things in two different ways, to actually prove that we always get well-defined arithmetic and that the laws of arithmetic are satisfied. This requires, well, perhaps an axiomatic framework in the spirit of Euclid. In the spirit of Euclid, not these far-fetched modern variants like ZFC. So the challenge is to try to set up a geometry where you end up having the laws of arithmetic as theorems, which depend on prior, more fundamental laws or statements. And to try to understand the situation so that, as Euclid did, you've pared things down to the simplest essential assumptions that are required to set up the theory. It's an interesting challenge, so that we get an affine geometry sufficiently rich to support rational number arithmetic. Okay, so we have an affine or projective geometry closely associated with the more familiar arithmetic of the rational number line. Of course, those who've studied Euclidean geometry will know that when you're doing Euclidean geometry and you have a compass that allows you to make more constructions, then, well, certain kind of irrationalities start to appear, or appear to appear. And of course, the ancient Greeks had a lot of problem incorporating these irrationalities into their conception of arithmetic with geometrical segments. This is a kind of very interesting chapter that we're going to talk about next time, is the arithmetic of the rational numbers, first of all, and then going beyond it to start to address the very big challenges that were confronting the ancient Greeks. In fact, the Pythagoreans started to wrestle with irrationalities. And this difficulty with irrationalities really is a long shadow that even casts its shadow today on modern mathematics. We have not solved the problems that the Pythagoreans uncovered. This is a remarkable but important insight to realize. All right, so we're just getting going here on this very, very important problem. It's going to be interesting. We're going to touch base with lots of interesting historical mathematics, and I'm going to have to be a little bit critical of the modern sort of fairy tale approach to the continuum that we currently have, that most students, including maybe many of my viewers, will have been indoctrinated into. All right, so it's very important to keep an open mind, to try to figure out things yourself. Don't be too swayed by fashion or numbers or appeals to authority. Okay? Scientific, logical reason should be what's driving the discussion here. All right, so in our next video, we're going to carry on with this. We're going to look at irrationalities from the Greeks and forwards. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.